The last topic in this presentation, okay, will be about okay, how we can model registers and counters. For some reason here I have yeah. So let us see how we can model registers and counters. This will be, in fact, the last topic in this presentation. Let me start with a register that has a parallel load. So we know what a register, okay? We already have seen that before. We have studied registers. So how do we model this in Verilog? I don't really want to model this as a state diagram as we have seen in the previous examples. It will be easy to model this. We can model the behavior of this register. It's very easy. Now you might want to make it parameterized. I would like to have actually a parameter n. Here, okay, n is a parameter. It has a default value, which is 4. This will be for a 4-bit register. But really, when you would like to instantiate this register, you might assign a different value. When you instantiate, you might choose a different value for n. And you can instantiate an 8-bit register, a 16-bit register. So n can grow. It can be like 8 or 16. So for this reason, we need to have the input data as a bit vector from n-1 down to 0. So we are relating the input data to the parameter n. Okay. So it's n-1 down to 0. So it's an n-bit vector. Load is just one input here. This will actually indicate that whether you would like to load the data inside the register or you don't really want to load. There is a clock input and there is a reset. So don't forget these inputs, clock and reset. There is the output. The output itself is a bit vector. It consists of n bits because this is an n-bit register. Okay, so it's n here is my parameter. So we can describe all of this register using just one always statement, as shown here, which is sensitive to the positive edge of the clock and the positive edge of reset. Because the reset appears in the sensitivity list, we can reset at any time. And this is why the reset is asynchronous. It's not synchronized with the clock. So if we have the positive edge of reset, if this is true, then data out becomes 0. So basically, we are clearing all the flip-flops. Remember that here data out consists of n bits, not just 1 bit, but n bits. Else if we are loading, then data out becomes data in. We are loading the input data into this register. Okay, by doing this kind of assignment, we are loading the data. But this is if load is equal to 1. So if we are not resetting and we are loading, then we are changing the data out to become data in. Now, there is no final else here. Why? Because there is no change. And if you are not resetting, if you are not reloading, then there is no change in the flip-flops. And this is why there is no need for a final else. We can simply discard this else. It will remember. Okay, this always statement is describing a memory element. It's describing a register, and therefore is going to remember the old value of data out. We are using the flip-flops to store, okay, the value of data out, and therefore there is no change in data out. Make sure that the output is of type register, because you are doing this procedural assignment to data out inside the always statement. Okay, so make sure that it's of type register. Do you have any question about this? This is how we can model a register with parallel load. I only have few remaining slides, in fact, how we can model a shift register, how we can model a counter with parallel load, up-down counter, okay, writing a test bench and verifying things. This is a shift register. You can see that the Q output is connected to the D input of the next flip-flop. Now, what is the direction of this shift? Is it shifting to the left or shifting to the right? How are we shifting? Students, I need you to answer this question, please. Are we shifting to the left or to the right?
To the right.
Yes, to the right. Simple. You can see that. So basically, the Q output is connected to the D input of the next flip-flop. So this is like shift to the right. We are shifting to the right. Yes. Now we can model this in Verilog very easily. So you can see that this is my module, which is called shift register. It has a parameter. Now it's good to have parameters in Verilog because you can use the same description to describe modules that have different slices. Yani, for example, here n is specified as my parameter. It indicates an n-bit shift register. And you can have the default value to be equal to 4. But when you instantiate it, you can change the value of n. You can make n equal to 8 or 16 if you would like to have an 8-bit shift register or a 16-bit shift register. So you can easily change the value of n when you instantiate this module. So this is the benefit of using parameters in Verilog descriptions. So we have data in here is my input. So data in here is a single bit. You have a clock, okay, and we have reset. So these are my inputs here, okay, to my module. And there is only one output here, which is data out. So this is like serial in, serial out, shift register. Now inside this module, we have a queue, and the queue is described as a bit vector. Okay, that has n bits. Notice that how I'm using here n-1 down to 0. So the parameter n appears, okay, when we specify the size of a queue. And notice the type is register because we are using it like a variable. Okay, like we have variables in high-level programming languages, we can store a value in a queue. So here we have a queue consists of n bits. So this is describing n flip-flops inside my shift register. We are describing it with this declaration, with this queue. So we can number these flip-flops or these queue outputs. So this will be Q0, this will be Q1, this will be Q2, and this will be Q3. Okay, so you can see that we can number them. And if we have, let us say, n bits, we can go all the way to Qn-1. So Q0 here is my least significant bit. And in this example, Q3 is the most significant bit, okay? So we are shifting the bits from the right, sorry, from the left to the right. And this is a right shift, this is a right shift register. I can assign here data out to be Q0. This is a simple continuous assignment. So basically Q0 is my data out. That's what it means. And we can describe the behavior of this shift register using an always block as indicated here. So it is sensitive to the positive edge of the clock. So the changes will happen at the positive edge of the clock. But the reset here, notice that the reset has inverted input. So basically the input reset is inverted. So we are using the negative edge of reset. So this reset is asynchronous because we can reset at any time. The always statement is sensitive to the negative edge of reset. So when it sees the negative edge of reset, if not reset, it means the reset equal to 0. Then we are resetting, and therefore Q becomes 0. That's the negative edge of reset. Else, if we are not really resetting, then the Q becomes data in Qn-1 down to 1. Okay, so this is basically how we are doing the shifting. We are doing the shifting using this procedural assignment. So this Q here, which is shown, is a Q. It's a bit vector. It is Qn-1 down to 0. That's actually Q. Okay, so it consists of n bits. Now the most significant bit here, which is n-1, it becomes data in. So what we are doing is that we are assigning here. So for example, if n is equal to 4, then n-1 will be 3, and therefore the Q3 becomes data in. And the Qn-2 becomes a Qn-1. So what we are saying is that the Q2 becomes a Q3, Q1 becomes a Q2, and the Q0 becomes Q1. So this is basically how we are describing the shifting. We are describing the shifting with this assignment, with this procedural assignment, and the bits are shifted inside these curly brackets. Okay, this is the concatenation operator. So we are concatenating data in with the most significant n-1 bits of a queue. Okay, and by doing this assignment to the new queue, so this change of a queue will happen at the positive edge of the clock, because you see that the always statement is triggered at the positive edge of the clock. So this is how we can model, okay, a shift register in Verilog. The description is very simple. Once you understand the concepts, then you can really describe anything that you want in Verilog. Okay, this is just one example. I'm going to show you more examples, but please raise questions. Okay, if you have any question, you can just stop me and interrupt me, and you can raise your question. Is this clear? This is just one example. I'm going to show you more examples. Right, so let me now go to the next slide and show you how we can model a counter. Okay, we have seen counters before, okay, in a previous lecture. I'm going to show you how we can model a counter in Verilog. This is a 4-bit counter, okay, which has a data input here, which is D3 down to D0. It has a load input. So this counter has a parallel load. Okay, so if load is equal to 1, we are going to load the data input inside this counter. You can see the output of this counter, okay, are Q3, Q2, Q1, and the Q0. These are the outputs. These are the same as the outputs of the flip-flops. So inside this 4-bit counter, there are 4 flip-flops, and these are the outputs of the flip-flops. So the outputs of the flip-flops are the outputs of this counter. So we have enable input. We also have a clock input, and there is a C out here, which is an output. The importance of C out, as we have studied in a previous lecture, is that if you would like to cascade multiple 4-bit counters, you can connect the C out of one 4-bit counter to the enable of the next 4-bit counter. So therefore, you can cascade them. Okay, so that's the importance of having a C out output. Now, how do we describe this in Verilog? If you would like to generalize this to make it generic, you can use a parameter n. So therefore, you can use it not to describe only 4-bit counter, but you can make n equal to 5 bits, 6 bits, whatever number of bits. Okay, so the default value here of n is equal to 4, but you can change it. Okay, if you would like to double it, for example, make it an 8-bit counter, you can do so very easily when you instantiate this counter. Right, notice that the inputs here are D. D is my n-bit input, n-1 down to 0. We have the load input, we have enable, and we have clock. So all of these are inputs, okay, to the counter. The outputs, we have the Q output, which is also an n-bit vector, and we have the C out. Okay, so these two are the outputs of this counter. Now, C out, I can describe this C out very easily using one continuous assign statement. So we get C out equal to 1 when all the Q outputs are all 1s, and enable is equal to 1. So if I have enable equal to 1 and all the Q outputs are all 1s, then this is when we get the C out equal to 1. So I can describe this with a simple expression. I can say that C out becomes, so we're assigning this C out to become, now this here and Q, notice the end appearing before the Q. Now this is reduction end. So we are reducing all the bits of a Q. For example, if n is equal to 4 bits, then Q will have only 4 bits, Q3, Q2, Q1, and Q0. So this end reduction is going to end all the 4 bits of a Q. So it will be Q3 and Q2 and Q1 and Q0. In general, if Q has n bits, it will be the reduction of all the n bits of Q. And then we need to end it with enable. So we have another end here. Okay. So this end here is going to end, okay, the result of ending all the bits of a queue with the enable. So enable must also be equal to 1 to get the C out is equal to 1. So this is when we get C out. So when we reach the maximum count, which is 1111 or 15 in decimal, and it is enabled. Okay, so that's the meaning of C out. So notice that C out, we are describing it with a continuous assign statement, whereas the output queue is being described by this always block. Okay, to define the output queue, we are describing it with this always block. Now, this always is sensitive to the positive edge of the clock. Notice that the clock here, okay, this is the clock input. Okay, so this is the clock input to the 4-bit counter, and it is the input to all the flip-flops that appear inside this 4-bit counter. So the changes in the Q output will happen at the rising edge of the clock. So we're using here the positive edge or the rising edge of the clock. This is when we change the output Q. Now, what we have to do first is that we have to check this load input. If load, it means if load is equal to 1, if we are loading, then we change the output Q to become D. So notice that Q becomes D, and we are loading the value of D inside, okay, the counter. Okay, so that's you can load at any time. So when load is equal to 1, you can change the value of this counter to become the D input. Else, it means that we are not loading. You have to check this enable input. If this enable is equal to 1, then a Q becomes a Q plus 1. We are counting up. Okay, we are incrementing the counter, but this will happen again at the positive edge of the clock. Now notice that this if does not really have an else. There is no else here because we don't really need it. Okay, if we are not loading and we are not really enabling, then there is no change in the output Q. So therefore, if there is no change, we don't really have to say that the Q becomes a Q. Okay, there is no need to say anything. Okay, it means that do nothing. Okay, so for this reason, we don't really change the output Q. So if we don't really change the output Q, so we are going to save the output Q inside, okay, the flip-flops, because the flip-flops here will be memory elements. So for this reason, we are defining the output Q to be of type register, because we are using here, you can see that it is we are saving, okay, the value of the counter inside the flip-flops, inside the 4-bit counter. So this is why Q must be of type register, okay, like a variable in a high-level programming language. And we are using here, you can see the non-blocking assignments, okay, to assign to Q. And if you don't assign anything to Q, then this will not really change the value of a Q. It will remain the same. So therefore, it's going to remember what was the last value of a Q if you are not going to change it. So this is basically how the flip-flop works. So we are describing flip-flops inside this 4-bit counter. Right, so this is just one example about how we can model a counter with a parallel load. Do you have any question about this? Right, my next example will be how we can model a generic up-down counter. Let us make it actually slightly more fancy. Okay, we can have not only counting up, but we can actually have different functions. I can define here f as my function input. It consists of 2 bits. So we can define 4 different functions. So for example, f equal to 0, this will disable the counter. F is equal to 1, we count up. F equal to 2, we count down. And F is equal to 3, we load the counter with this data in. So here f equal to 3 is like my load input, okay, that will load the counter with my data input. There is a clock here, a clock input that will indicate when to change the value of this up-down counter. There is a count output. This is my count output. There is also a reset input. If I would like to reset at any time, I can reset the count back to 0. And I can make this reset an asynchronous reset. That can be done very easily when we describe, okay, this counter in Verilog. So this is my module, which is called UpDown Counter. It has a parameter, which is n, and it has a default value, which is 16, but you can change. Okay, this when you instantiate this UpDown counter, you can choose a different value of n. Right, so it's an n-bit counter, and therefore my data input will be n-1 down to 0. That's an input. I have a function input, okay, that consists of 2 bits, 1 down to 0. It does not depend on n. It is just actually a 2-bit function. There is a 1-bit reset and a clock. Okay, and the output here count consists of n bits, n-1 down to 0. And notice the type is of type register, because I would like to save the count inside this register. Okay, so this is why it's of type register, and you can see that we are assigning to this count using procedural assignment. We can easily describe it. We can describe the behavior of this UpDown counter using an always block. Notice that this always is sensitive to the positive edge of the clock and the positive edge of reset. So you can see that the reset appears in the sensitivity list. So if we are resetting, then count becomes 0. We can reset at any time. So even though we don't have the positive edge of the clock, if we have the positive edge of reset, this reset will be equal to 1, and we can reset at any time. And we can skip all the else if parts. If we are not resetting, then we have to check the function f. So we have here else if f is equal to 1. It means I would like to count up. So count becomes count plus 1. Notice that this is a procedural assignment, because we are assigning to count using a procedural assignment. This is the reason why count should be of type register in the output. Okay, else if f is equal to 2, I would like to count down. So this is count equal to count minus 1 becomes count minus 1. Again, procedural assignment. Else if f is equal to 3, then here I would like to load data inside my counter. So therefore count becomes data in. This is basically just loading. Okay, loading the data. This is my parallel load. This is when f is equal to 3. Now notice f equal to 0 does not really appear. There is no else if equal to 0, f equal to 0. Why? Because we are disabling the counter. So when we disable the counter, nothing happens. So the value of the count does not really change if f equal to 0. So I don't really need actually a case here in which else if f equal to 0. There is no need for that. We can just simply say that there is no change in the value of count, but the count itself is implemented using flip-flops. So therefore, it's going to remember the old value of count, okay, when there is no change, okay, in the count value. So you don't really have to write that count becomes count, okay? Yani there is no need actually to write something like this in Verilog, and you don't need to handle this case, else if f equal to 0. There is no need for that. Okay, so that's basically my model of a generic UpDown counter. Okay, and it can work actually for any n. Yeah, you can change the value. You can make a small counter, a large counter, depending, of course, on your design. Okay, students, do you have any question about this? Right, we can write a test bench. Yeah, to finish this example here, I wrote a test bench, okay, for this UpDown counter just to test it and to verify its correctness. So I wrote this module, which is UpDown Counter Test Bench TB here for test bench. So it has here, I'm going to instantiate this UpDown counter. Now I would like to choose here n to be 8. So this is here my parameter n. So I chose 8. Okay, so therefore the value of n will be 8. Okay, in this specific instance. And this is called here my test counter. Okay, it's just given a name for the instance. It's called test. It has data in. So the data in must be 8 bits. So you can see this is 7 down to 0. The function f must be 2 bits. So this is 1 down to 0. So we have a reset, we have a clock, and we have the count output. You can see that the count here is of type wire. Okay, so this is basically my count output. Okay, it's an 8-bit count. So basically, this is the output of my UpDown counter. Now, what we need to do is that we need to provide some input. Notice that the inputs here are of type register, like the same thing like variables. Okay, so you can change them inside the test bench, and you can watch the output count, okay, to verify the correctness of the counter. So I can initialize, for example, my data in. I can use here the initial statement to initialize my data in. Okay, I can initialize it in hexadecimal. It consists of 8 bits, which is 2A in hexadecimal. Remember that each digit in hexadecimal is 4 bits, so we need 2 digits for 8 bits. So this is my initial value for data in. It will be just the same value throughout the simulation. We're not going to change data in. I need to generate a reset pulse. So we can say that, for example, at t equal to 2 nanoseconds, okay, if I'm using the time scale to be nanosecond. So we are going to make reset is equal to 1. And then after 4 nanoseconds, so we add 4 plus 2, this will be at t equal to 6. Then reset becomes 0. So reset is going to jump to 1. That will be the positive edge of reset at t equal to 2. And at t equal to 6, then it's going to go drop from 1 down to 0. Now the pulse, the width of this pulse will be 4 nanoseconds. Okay, but it's going to drop, okay, at t equal to 6 nanoseconds. So we add the 4 plus the 2 here, then this is actually how we know when it's going to change back to 0. We need to generate the clock. Initially, the clock is equal to 1, so we use the initial statement to initialize the clock. It's very important to initialize. And then after that, we use the always to generate my clock, which is a periodic signal. Now I can choose, for example, here #5, indicating that every 5 nanoseconds, clock becomes not the clock. So we are inverting the clock every 5 nanoseconds, and therefore the clock cycle will be 10 nanoseconds. So it's 2 times 5. So we'll have 5 nanoseconds, the clock is 1, and another 5 nanoseconds, the clock is 0. So 5 nanoseconds, 1, 5 nanoseconds is 0. So the clock period will be 2 times 5, which is 10 nanoseconds. And that is going to repeat. So the always here is going to ensure that this clock will be generated in the simulator. So this is my clock input. And finally, we need to provide a function, f. So at t equal to 2 nanoseconds, we are going to provide f is equal to 3. This is when I would like to load, okay, my data inside the simulator. And this is my data in here, which is 2A in hexadecimal. Then after 10 nanoseconds, so this will happen at t equal to 12 nanoseconds, f becomes 1, it means count up. Then we can actually delay it by 30 nanoseconds. So this is my delay here, which is shown 30. So 30 here means 3 clock cycles. So I would like to keep f equal to 1 for 3 cycles. So delay f equal to 2 by 30 nanoseconds, and then delay it by 10 nanoseconds and make it f equal to 10, and delay by 10 and make f equal to 1. So what is shown here is the delay of these statements, and these are all procedural assignments in Verilog. Now we can run the simulator. Okay, so you can see that how data in is initialized to 2A in hexadecimal. It's going to remain 2A throughout the simulation. Now notice the reset. How we have this reset pulse. So it's going to jump to 1. Okay, so initially it's uninitialized, so it's shown in red. But then at t equal to 2 nanoseconds, it's going to jump to 1. And then after 4 nanoseconds, going to drop. So we delay it here by 4. So at t equal to 6 nanoseconds, going to drop back to 0. Notice the clock. The clock has a clock cycle or a clock period, which is 10 nanoseconds. So 5 nanoseconds, the clock is 1. 5 nanoseconds, the clock is low. And you can see the clock, it's a periodic signal as shown here. Now, what we need to do is that we need to change the value of the function f and see the output count. So initially, I have this reset. So this reset is going to force the count to be 0, 0. We can reset at any time. We don't really have to wait, okay, for the rising edge of the clock. So I can reset and make it 0, 0 initially. Then I have my function f is equal to 3, but we'll wait for the next rising edge of the clock. So 3 means load data. Okay, that's what it means. So therefore, we loaded data inside the counter. So the count becomes 2A, which is the value of data in. So we are changing it from 00 to 2A. That's the value that we have loaded, the 8-bit data that we have loaded inside the counter. Then we wait until the next clock cycle here, the next rising edge. We see that F is equal to 1. Notice that's going to remain 1 for 3 cycles because we are delaying. Okay, so we put actually hash 30 to delay, okay, the changes in F by 30 nanoseconds. So notice that in the next cycle, okay, is going to be, so it's 1, it means that we increment the count. So it was 2A, it became 2B. The next cycle, we increment the count again, and then we increment the count. So 2B, 2C, 2D, for 3 consecutive cycles, we are incrementing the counter. Then after that, I would like to decrement the count. Notice that the function F became 2. So we wait until the next rising edge of the clock, which is here, and then we decrement the counter. So the count will become 2C. So it went down from 2D to 2C. That's decrementing the counter. Then next cycle, F is equal to 0. You can see it's equal to 0. So we're going to keep the counter unchanged. So it's going to remain here 2C for another cycle. So 0 means there is no change. Okay, do nothing. That actually is the meaning of 0. Do not change the value of this counter. Then I would like to increment it again. So I'm going to make F is equal to 1. Wait until the next cycle and change it from 2C to 2D. And then as long as it is continues to be 1, then we continue to increment it. You can see that how we are incrementing the count. Cycle by cycle, we are going to increment the count. So this way we have verified the correctness of this up-down counter, and these are the waveforms. And this is my last slide in this presentation. Okay. So you have any question about this? So this is what you really need to know about Verilog. So we have studied Verilog in this course, and we have seen how we can model not only combinational circuits, but also sequential circuits. Okay, so Verilog is really a powerful, okay, hardware description language. It's very useful, okay, for circuit designers, okay, when they would like to model, okay, their circuits and verify their correctness. We can actually model something which is, so what we did is that we modeled the behavior of the counter. We describe it with always. Some outputs we use continuous assignment. You can mix, okay?